right? It actually is the same way of doing as the previous methods, like all the basic version. So meaning from 1 to 2 is still just isentropic compression. 3 to 4 is just another round of isentropic compression. And here also isentropic expansion, which also indicates that, now okay, assumption, this one don't forget. Now, and then here we show you how to get the pressure ratio. Now, then very important part at the following part. So you see, 4 and 2 are at the same temperature, right? 3 and 1 are at the same temperature. 6 and 8, same temperature. 7 and 9 also same temperature. When you are dealing with gas or ideal gas, temperature is the only thing that inside the enthalpy. Which also means that T1 equals to T3, H1 is equal to H3. And etc. T2 equals to T4, H2 equals to H4, T6 equals to T8, T7 equals to T9, H6 equals to H8, H7 equals to H9. Which also means, actually this is the exact same as just solving the normal Brayton cycle, because you only need to do one time. The values are the same. So, first you start from state 1. So state 1, T1 equals to 300 Kelvin, H1 is 300.19 kilojoule per kg if you read the table. Then if this is, so since this is, we are using the variable specific heat method, then you find PR1. If constant specific heat method, then you use the isentropic relation or the equation. So from PR1, then same method, you find PR2 using PR1, then go back to table A17, obtain T2, then from T2 you can get H2. So then you are done with the left hand side, because 4 equals to 2, 3 equals to 1. Then you repeat the same thing for 6. So T6 equals to 1300 Kelvin, H6 is 1395.97. Then you find PR6. Then from PR6 you find PR7. You get T7 and H7. So can you see this is exactly the same as how you just solve the normal Brayton cycle. That's why I say don't overthink things. Just see what are the values that you have, solve it accordingly. So these first two steps, is everyone clear? Does anyone still need the previous slide? No? Then I'll go move on, okay? Now, so now that you have all the H, right? Then once again, you can go back to calculating all the backward ratio in thermal efficiency. Now, so here you can also, since they are the exact same value, in a way you don't need to calculate again also. You just need to find H2 minus H1, multiply by 2. Then you get 2 compressor work. Because again, these two are the same thing. So find this, then you multiply by 2, you get 2 compressor. Just don't forget that you have 2 lah, basically. Then work out from the turbine also same thing. Get the work out from H6 minus H7. Then you multiply by 2. So you get the work out value. Then work net is just their net value. So again, Q in, don't forget that you have 2 Q in this case as well. So then Q in you cannot times 2 lah. So Q in is just H6 minus H4, H8 minus H7. Okay, so H6 minus H4, H2 minus H7. So from there you obtain Q in, then you can calculate backward ratio, you can calculate thermal efficiency. So remember that we mentioned that if you are using only intercooling and reheating without regeneration, we say that backward ratio will improve, but thermal efficiency will drop. So you can see that since this question is based on 1300 Kelvin and 300 Kelvin, we can compare with the previous example. But we need to pick the ideal one because this question is based on the ideal cycle. So where is the ideal cycle? Okay. So if you compare to the ideal cycle, you can see that the thermal efficiency here is 42.6. And just now what we got was 30 something. So you can see that the thermal efficiency has dropped in this case. Do we have a backward ratio? So thermal efficiency has dropped. As for backward ratio, so the backward ratio here is 40.3 or 0.403, while the one that we calculated just now was 0.304. So it has also dropped by 10%. But for backward ratio, we want the value to be low rather than high. So you can see that backward ratio has improved by about 10%, but efficiency dropped by also about 9% or 8%, about there. Maybe, is it 42? Yeah, 7 now, I think. So here you can see by using intercooling reheating, RBW improved, thermal efficiency reduced. Okay, so this is part A. So then part B, we incorporate 100% effective regenerator. So when we incorporate, let's say when we add in the regenerator into the system, unlike ranking cycle, when you add regenerator into this system, it actually doesn't affect the turbine output or input because you are just using the exhaust. You didn't purposely channel out a portion of the gas. So it doesn't really affect the work out and the work in. So which means everything that you use here actually is still applicable. You just need to change one value, which is Q in. Because that's the only thing that changes when you use regenerator. Q in has reduced when you use regenerator. So for part B, what we do here is we recalculate the Q in. Of course, if the effectiveness is not 100%, then it becomes a bit more complicated. But now that this is 100%, which means that the new Q in is from 5 to 6 and 7 to 8. Which also means actually you can times 2 also because you can see the value is exactly the same. So now this is the new Q in when you have when you have the regenerator. So with this Q in, then you have a new Q in, and you can see now the thermal efficiency improves. So this is also much better than the ideal case where you don't do anything to the system. But of course, this is from a 100% effectiveness regenerator. So you can see that the thermal efficiency almost doubles as a result of regeneration compared to the no regeneration case. The overall effect of two-stage compression and expansion with intercooling, reheating, and regeneration on the thermal efficiency is an increase of 63%. So the increase of thermal efficiency is about 63%. Okay, so just something slightly extra here. If the effectiveness is not 100%, okay, so let's say if the regenerator effectiveness is not 100%, then your value 5 will be somewhere here. So then in that case, you need to calculate the new H5, the new 5 based on the effectiveness equation first. So which is so what was the effectiveness equation? Let's see. Where was it? So you need to use this equation here. So even though it is a reheating and intercooling, you are still only focusing on the first one because you are only reheating that part using the regenerator heat, which means it is still H5 minus H2, H4 minus H2. So in this case here, it will be, where is it? same thing. So at the top is H5 minus H2. So this H5 is the mu 5. Then at the bottom here is either H7 or, sorry, not 2, it's 4. So at the bottom will be either H7 or H9, doesn't matter because they are at the same level, same value. Okay, so the regenerator will only affect this section, it won't affect this section. So which is why here we are still basing on here. So this will be H5. Let's say if this is not 100%, then this H5 minus H4, then H7 minus H4, or H9 minus H4, same value. Then only you recalculate the Q primary and Q reheat using the H5, new H5. Okay, so just one extra step. And if you have one that is not 100% effective. Okay, other than that, nothing much here. Any question for this example? Okay, so now that we are done with all of this, I will show you some of the different type of power of turbine or gas power turbine that you will see, but we won't study them like in detail, just some different type. So so sometimes you also have arrangements such as this. So the turbine is usually arranged to drive the compressor. So sometimes, like we do just now, right? We have the turbine that will drive the compressor, then whatever the leftover we channel it out. So sometimes we actually might make something that with 2 turbines instead. But this is not a reheat cycle. It's just that you can see from the diagram here, you have 2 turbine here. So 1 turbine, 2 turbine. This turbine we use it solely, is solely dedicated to powering the compressor itself only. So then that's why now if in an actual case, of course if it is ideal it will look different. If it's ideal we just go straight down. Actual one you can see that then now you have 2 levels because you have 2 different turbines. And then since the first turbine is used to mainly power the compressor, then you can just say that the change in enthalpy from 1 to 2 is actually the same as 3 to 4. Because this turbine has no other function other than powering this. Then after that, the rest we use another turbine to power a generator. So this is one. So we are showing you like different type of configuration basically for different purposes. So this one network output is easier to calculate because you only need to focus on the second turbine. You don't need to focus on the first turbine because they will just cancel off. And also for an aircraft engine, sometimes you also have this kind of different type of configuration whereby the first one, actually the first one was what I showed you in the video just now, but without the diffuser. This one we only show the nozzle. Then at the bottom is a turboprop engine. So this one will have a propeller, but other than that, actually everything is the same. It's not actually everything is the same. Then we also have what we call a parallel flow unit. So this one we have two different combustion chambers. So then these two will have different. These 2 combustion chambers go to 2 different turbines. Then you get 2 different applications out of that. So like the first one for other purposes, second for other purposes. So the power turbine operates independently of the compressor and turbine. Actually, this one, the first one was used to drive the compressor. Then the second one is for net power. But now we use 2 combustion chambers instead. So again, it's just a variation of what you have learned, just different type. Okay, so now I show you one complicated, not more complicated design. I won't show you the working, but I'm not saying that it will come out this time because I haven't decided yet. I haven't said anything for you guys yet. But I asked one batch this question for test before. I think most of them cannot do that time. No, actually, the smarter students could understand, but they also mix up mistakes with it. That's the only difference. But yeah, so this is what we call a combined gas vapor cycle. So what we are trying to say here is we combine both of them. both of the cycle in order to generate in a way more power. So a popular modification involves a gas power cycle topping a vapor power cycle, which is called a combined gas power cycle. So the best combined gas cycle is the Brayton combined with Rankine cycle, and this will give you a higher thermal efficiency. And the combined cycle increases efficiency without increasing initial cost greatly, and the which efficiencies are over 50%. So what happened here is actually something like this. Obviously, the graph here is not 100% correct because the first, this part here is gas, right? And the bottom one is water vapor. So obviously, this gas is not supposed to be under the saturation line lah. But since we are dealing with two different, how should I say? Since we are dealing with two different substances here, you can also view it as, you know, you have two different axes. One is actually for this, one is actually for this one. So actually it's the same thing. If you look at this, that might look a bit complicated, but if you look at this, actually it's the same. So basically what you have here is this. It should start from here. So the first one you draw in here to a compressor. So Brayton cycle, right? A compressor. So it goes to combustion chamber. So here you need to burn. You need to add fuel here. Then it goes to the turbine. So this turbine will generate power. We have got output. Then instead of a regenerator like we did just now, we connect this to the heat exchanger for the Rankine cycle instead. So Rankine cycle from here, water then just go out, got heat up, goes to the steam turbine, turbine generate more output. Then it goes back to the condenser to release heat. Then back to the turbine again. So actually, look, if you want to solve this, it's the same thing. You do Rankine cycle, you do Brayton cycle. Just that at the heat addition part, this Q out from here is actually equals to Q in here. That's all. But it looks complicated lah, but can do one. Okay, so this one just wanted to show you here that we have this kind of cycle. Alright, so we are actually done with this chapter. So this chapter is not too long because again it is actually just a repeat of Rankine cycle, but we changed the whole thing into gas and then we do. So instead of spending too much on the lecture, again this time you can see I don't have as much example for you to try as well. So which means next week we will focus fully on the tutorial for both classes.